Je ne suis pas high. All right, so here we are. Let's see, that's chapter 2. We're going to need to be at chapter 3. FYI Assault. It'll be the next page. And there's a summary. Here's the end of chapter problems. So let's get kicking. Chapter 3. First up, problem 30. Come on, where's that? There we go. All right, problem 30. Which of the following drawings is more likely to represent an ionic compound and which a covalent compound? All right, so remember, oops, let me, boop. All right, so which of the following is more likely to represent an ionic compound and which a covalent compound? The one on the left is ionic, the one on the right is covalent. Remember, ionic compounds, they always come in a ratio. They form a great big network, and covalent compounds come in individual molecules. So here we have our network of alternating positive and negative ions, and here we have a whole bunch of separate molecules. 32. Where on the periodic table would you find the element that has an ion with each of the following electron configurations? Wow, that's a loud car. Okay, or a motorcycle. Identify each ion. 3 plus ion, 1s2, 2s2, 2p6. All right, so 1s2, 2s2, 2p6 brings us here to neon. It's a 3 plus ion, so 1, 2, 3 more brings us to aluminum. B is argon 3d3. It's a 3 plus ion, so argon is 1 below. And so the S2, 1, 2, 3. It's lost its s electrons, and it's lost one more d electron. So that means it is this one here. I believe that one is not manganese, but chromium. Yes, that would be chromium. But let me be certain. Let me pull up periodic table. 1, 2, 3, 4. Yes, that's chromium. I am good. I am very good. 2 plus. Krypton 5s2 4d10. So argon, krypton, 5s2 4d10. It is a 2 plus ion. It's in the p block, so it loses p, then s, so it has lost 2 p electrons. It's this guy here. I believe that one is lead. No, not lead, 10. That's 10. 5s2 4d10. Yes, 10 SN. And finally, 1 plus krypton 4d10. Okay, krypton 1 plus 4d10. Oh, okay. Excellent. Okay. So 4d10 means we're looking at silver. Silver ordinarily is 5s1 4d10. Remember, it promotes that s electron up into the d subshell to give it a full subshell. So it has a full subshell, but it has lost that single s electron. Ooh, that was good. Well done. Well done. All right, now number 34. Each of the following, A through D, represents one of the following substances at 25 degrees Celsius. Sodium, chlorine, iodine, and sodium chloride. Okay, so sodium is a solid metal. All the atoms are going to be the same, so that's going to be B. Chlorine, that's diatomic molecules, and it's going to be a gas at room temperature, so that's going to be D over here. Next up, iodine, also diatomic molecules, but it is a solid at room temperature, so that's going to be A. And of course, sodium chloride is going to be C, alternating ions. I believe next is 36. Yep, 36, 38, 40, 42, 46, 44, 46, 48, 50, 52, 54, 56, 58, 60, 62. So we're just going to be doing all of the even-numbered problems until we get to 62. Okay. So 36. The 3 binary compounds are represented on the following drawing. Red with red, blue with blue, green with green. Give a likely formula for each compound. All right, so red with red. Let's see, we got phosphorus and not tin, but no, that is tin. Yes. Is that phosphorus? Can't tell. Let's see. No, that's below oxygen. So that's sulfur and tin. So I can think of 2 different compounds that you could get with tin and sulfur. The difference is, sulfur will always be 2 minus, but tin could be 2 plus, or tin could be 4 plus. So it could be tin 2 sulfide or tin 4 sulfide. So those are the two possibilities for the red. Oh, I didn't even plan that. All right, now let's do blue. Let's see, that's fluorine, and I think that is not magnesium, rubidium? Strontium. Yes, fluorine and strontium. So strontium is always going to be 2 plus. Fluorine is always 1 minus. So it is so the formula there is going to be strontium fluoride. And finally, green with green. Let's see, that's carbon, fluoride, chloride, bromide. Carbon bromide, CBr4. All right, 38. Write the formulas for the following binary compounds. Potassium chloride. Oof. I must have slept funny. My back is bugging me. All right. So, potassium chloride. Potassium chloride is just going to be KCl, 1 plus, 1 minus. B, this is problem 38, by the way, so 38. B is tin 2 bromide, so that's SN2 plus, Br1 minus, so SnBr2. Calcium oxide, calcium is 2 plus, oxide is 2 minus. Barium chloride, it's going to be BaCl2, 2 plus and 1 minus. And finally, E, aluminum hydride. Aluminum is 3 plus. As a negative ion, hydrogen takes a negative 1 charge, so aluminum hydride is AlH3. 40. Name the following ions. A is just barium. Barium, I hardly know him. CS1 plus is just cesium. V3 plus. Vanadium can take multiple charges, so we have to include the charge. So that's vanadium 3. HCO3 1 minus is bicarbonate or hydrogen carbonate. E and H4 plus is ammonium. F, nickel 2 plus. Nickel can make multiple ions, so that is nickel 2. NO2 1 minus, polyatomic ion, finally, is nitrite. Second row starts at 2. ClO2 1 minus, that is going to be chlorite. Mn2 plus is manganese 2. And finally, ClO4 1 minus is perchlorate. 42. What are the formulas of the compounds formed from the following ions? Ca2 plus and Br1 minus. Let's see, 42A. That's just calcium bromide. Ca2 plus and SO4 2 minus is calcium sulfate. C, aluminum 3 plus SO4 2 minus, that is aluminum sulfate. Just bring the charges down. So 2 minus, 3 plus, bring them down, and then if necessary, reduce. But 2 and 3, that's as low as that ratio can get. Fear. Do we have any? Nope, no questions. 44. Write formulas for compounds of calcium with each of the following. Calcium chloride, calcium oxide, and calcium sulfide. So that's just going to be calcium chloride, calcium oxide, calcium sulfide. 1 minus, 2 minus, 2 minus. 46. Give the formulas and charges of the following ions. Okay. So let's see, that's 44A, B, and C. 46. Can I fit? No, I cannot. 46. The charges of those ions. Let's see, sulfite is SO3 2 minus. Phosphate is PO4 3 minus. Zirconium 4 is Zr 4 plus. D-chromate is CrO4 2 minus. Acetate C2H3O2 1 minus. And thiosulfate S2O3 2 minus. Just think, you spend 20 years doing that, and you'll be able to do that on the top of your head too. 48. Fill in the missing information. Give the formulas for the following compounds. Na blank SO4. Oh, it's just what are the ratios? Okay, so 48A, it's going to be Na2SO4. B is Ba3PO42. Gallium sulfate. Well, that's not entirely. That is tricky. Okay, so gallium is right here on the periodic table. It can either lose its p electron to become gallium 1 plus, or it can lose the p and s to become gallium 3 plus. Now, this is the one we're looking at right here. So if it were gallium 1 plus, then it would be Ga2SO4. But that wouldn't. Oh, you can't see what I'm pointing at. So this is the one we're looking at right here. Gallium, if it were 1 plus, it would just be Ga2SO4, and you wouldn't need the parentheses here. You do need the parentheses, and you are going to have a subscript on sulfate. Therefore, it must be gallium 3 plus. Ooh, that is good. So that means it's going to be Ga2SO4 3. Okay, 50. What is the difference between a covalent bond and an ionic bond? A covalent bond is formed by the sharing of electrons. The covalent bond is located entirely between two atoms. The electrons are shared between the two of them. It is entirely local, highly directional, and it does not create charges. An ionic bond is created by the transfer of one or more electrons from a metal to a nonmetal, creating opposite charged ions, and thus creating the attraction between them. So an example of a covalent bond, the bond between carbon and oxygen in carbon dioxide. Example of an ionic bond, the electrostatic attraction between sodium and chloride in table salt. How many protons and electrons are in each of the following ions? So beryllium 2 plus. So beryllium, what are you doing there, dog? That wasn't the dog, that was the cat stealing my sock. Okay. Beryllium 2 plus has 4 protons. It started with 4 electrons, it lost 2 of them, so now it has 2 electrons. B, rubidium 1 plus. Rubidium is down here. Element 37 protons. It lost 1 electron, so it has 36 electrons. Selenium 2 minus, selenide. So selenium is here, element 34. It does 34 protons. It gained 2 electrons, so it has 36 electrons, the same as rubidium 1 plus. Gold 3 plus. Yes, gold can be induced to form an ion. So that means it has 79 protons, and it lost 3 electrons, so now it has 76 electrons. Okay. 54. What are the likely ground state electron configurations of the following cations? Lanthanum 3 plus. Well, okay, that's not the worst of the lanthanides. So lanthanum is here in element 57. So it starts out, so I don't remember what problem this is. Anyway, lanthanum Let me open up the camera. There we go. Lanthanum starts out as xenon 6s2 4f1. So to become lanthanum 3+, it has to lose all 3 of its valence electrons, leaving it with the same electron configuration as xenon. Next was silver 1+. Okay, so silver is one of the exceptions you have to know. So it is krypton 5s1 4d10. Okay. Remember, it promotes from S into D. So a silver 1+, it just loses that S electron, leaving it with 4d10. Happy as a cat with a sock to destroy. Finally, 10 2+. 10 starts out krypton 5s2 4d10 5p2 10 2+. Remember, p block metals lose p and then s, so it's going to be krypton 5s2 4d10. Okay, all right. That was 54. 56. What is the electron configuration of calcium 2+? And what is the electron configuration of titanium 2+? Okay, so calcium and titanium are right here, 20 and 22. I'm sorry, Sasha. Your older brother is sick, and therefore you don't have anyone to play with all day, so you're getting kind of stir crazy. I know. So, calcium starts out argon 4s2. So calcium 2+ is just argon. Titanium is argon 4s2 3d2. So titanium 2+. Our transition metals lose S and then D. So it's going to lose the S. It'll keep the D electrons. So it's just 3d2. You haven't been able to see a single damn thing I've been writing. I'm sorry about that. All right. So calcium it loses its S electrons, leaving it with the electron configuration of argon. Titanium also loses its S electrons, but it keeps the D electrons. There are 2 elements, this is problem 58, there are 2 elements in the transition metal series scandium through zinc that have 4 unpaired electrons in their 2+ ions. Identify them. Oof, that's different. All right, scandium through zinc. Their 2+ ions have unpaired electrons. Well, regardless, that means they're going to lose their S electrons. That's going to be scandium is, wait, only 4? Oh, that have 2 elements that have 4 unpaired electrons. Oh, okay. So I can't just identify unpaired electrons. I'm going to have to go through and, okay. So scandium 2+, I'm going to shortcut a bit. They're all argon 3d1. Titanium 2+ is 3d2. Vanadium 2+ is 3d3. Chromium 2+, 3d4. So that is one of them. Manganese 2+ is 3d5. I think that would be the other one. Fe2+ is 3d6, which definitely does. They should have said only 4 unpaired electrons. Well, then that would also be unclear. Nevertheless, 4 unpaired, 2 paired, 4 unpaired. Okay. So just to clarify, the reason for that is there are 5 orbitals For 3d4, that's just 1, 2, 3, 4. For 3d6, 1, 2, 3, 4, 5, 6. Okay. 60. Which group of elements in the periodic table has the largest EI1? I guess that's the ionization energy. I'm having trouble reading that. And which group has the smallest? Okay. That symbolism is unknown to me, so I'm going to go back. Well, okay. Either it is ionization energy or electron affinity. It says 1, so it's going to be ionization energy. So that's pretty straightforward. So the largest first ionization energy is going to be the halogens. Which group has the smallest? That's going to be the alkali metals. We're just looking at either end of the periodic table. They might be counting the noble gases, in which case it would be the noble gases have the highest, because that would be starting with core electrons. Good Lord, Sasha. You are going frickin' bug nuts. All right, 62. Which has the smaller second ionization energy, potassium or calcium? That is going to be calcium. The first ionization energy for potassium takes it down to argon, and then the second one would take a core electron. So that's a huge increase. And which has the larger third ionization energy, gallium or calcium? That would be calcium, because the first two from calcium are valence electrons. The third one would be core, whereas gallium has 3 valence electrons to lose, no problem. 3 atoms have the following electron configurations. Which of the 3 has the largest second ionization energy? Which has the smallest 7th ionization energy? Okay. Largest IE2. Interesting. So this here is a noble gas, so you're removing nothing but core. So I'm going to say that that one has the highest second ionization energy. And the smallest IE7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So either way, you're dipping into core electrons. But you ventured less far into the core. You've removed 5 electrons. Okay, so it's going to be, I think, A. That's interesting. Because with A, you've removed 5 valence electrons before you start dipping into the core. So you've removed the second core electron with that. With this one, you start right away removing core electrons. So it's just going to be enormous from the start. But on the other hand, these are all much closer, but it has a smaller nucleus. So I'm going to go ahead and say A. I want to check on that one, though. That is an interesting proposition. Interesting set of problems there for 64. I'll dip into the appendix. Answers to selected problems. Chapter 3, number 64. Argon has the highest and the lowest. Oh, it's the highest of, and the lowest. Interesting. Noble gas, highest and lowest either way. Weird. Okay, so let's think about that. So I was right. You start off removing core. It's going to be the highest, but 1, 2, 3, 4, 5, 6, 7. I guess the fact that it's in the core, you're not going to get a massive jump every time you remove from core. So I guess that kind of makes sense. All right, so let's go back to chapter 3. Was ist ein Salz? All right. That was 64. Yes, now we're on 66. Oh, wait. Was I not supposed to do 64? I think I wasn't supposed to do 64. All right. Yes, I was supposed to skip that one. And 66. All right. So number 68. Which element in each of the following sets has the smallest first ionization energy and which has the largest? Okay. Lithium, barium, potassium. Lithium, barium, potassium. Which has the smallest and which has the largest? Okay. Barium's furthest down, so it's going to be smallest. Lithium's highest up, so it's going to be highest. Boom. That was rather straightforward. Boron, beryllium, and chlorine. So boron, beryllium, and chlorine. So further right is higher. Further down is lower. So beryllium is going to be the lowest. Probably. And then chlorine is probably going to be the highest. That's an unpleasant comparison to have to make. Because down, lower, right, higher. But it's so much further to the right. I'm going to say chlorine is the highest and beryllium is the lowest. Calcium, carbon, and chlorine. Calcium, carbon, chlorine. Calcium is definitely the lowest, and I'm still going to say chlorine is the highest. All right. Who is next? 72. Which has the more negative electron affinity, sodium or sodium? Okay, the sodium 1 plus or neutral sodium. Electron affinity is the amount of energy you will get back if you add an electron. That's going to be sodium 1 plus. It has a positive charge, so you're going to get more energy back by adding an electron. Sodium 1 plus or... oh my gosh. Excuse me. Sodium 1 plus or chlorine. I'm going to say chlorine. Chlorine really wants that electron. Sodium doesn't quite so much want it. All right. 74. Why is energy usually released when an electron is added to a neutral atom, but absorbed when it's removed? All that but is unnecessary. There's no contradiction between those. Electrons and protons have opposite charges. The electrons are attracted to the nucleus. They're held there by the nucleus. So when you release a negative charge, it will fall toward a positive charge, releasing potential energy along the way, transforming it into kinetic energy. And thus you have to put energy in order to remove it. There's no contradiction there. That but that's a stupid but. 76. No element has a negative second electron affinity. Oh, okay. Oh, the process A minus to plus electron to is unfavorable for every element. So, oh, really? Well, that's because it has a negative charge, and like charges repel. I mean, that's a pretty straightforward thing. I would not have expected that, though. I would not have expected every electron affinity to be unfavorable. For every second electron affinity. Because, I mean, elements do form second 2 minus ions and 3 minus ions and so on. It does happen. Huh. I would not have expected that, but it's because negative charges, like charges, repel. 78. Order the following compounds according to their expected lattice energies. Lithium chloride, potassium bromide, magnesium chloride. Okay. So this is taking it a step further than I would have expected. I would have just done it pairwise, but they're going for a full set of 4. So, lithium chloride. Let me write these down. Lithium chloride, potassium bromide, and magnesium chloride. Well, magnesium chloride is going to be the highest because magnesium has a 2 plus charge. I mean, that's just going to outweigh everything else. So I'm going to put magnesium chloride at the top of the list. Higher lattice energy. Okay, so now lithium chloride versus potassium chloride. Well, potassium is bigger, physically larger. It has a larger radius than lithium, so this is going to be smaller. Then potassium bromide is going to be smaller still because chlorine is smaller than bromine. Bromine is bigger than chlorine. So lithium chloride because lithium is the smallest, smaller of the two positive ions. Then potassium, chlorine, then potassium, and bromine, because bromine is bigger than chlorine, so it has a smaller lattice energy. You can always be surprised. All right, who's next? Oops, not you. You. 100. Going ahead quite far. Oh, 2 pages even. Okay. Copper 1 plus has an ionic radius of 77 picometers, but copper 2 plus has an ionic radius of 73 picometers. Again, that but is totally unwarranted. You would expect a more positive ion to have a smaller ionic radius. As you remove electrons, the ion just keeps getting smaller and smaller. There is less repulsion among those electrons that remain. So the protons are able to pull harder and harder on the remaining electrons. On top of, let's just leave it there. The more electrons you remove, the less repulsion there is among the electrons that remain, and it can pull harder. So you would expect copper 2 plus to be smaller than copper 1 plus. Next up is, I believe, 108. Yes, 108. Oh, and then 109, then 118. 108. Each of the following pairs of elements will react to form a binary ionic compound. Write the formula of each compound formed and give its name. Okay. So magnesium and chlorine is MgCl2. The name is magnesium chloride. Then calcium and oxygen is just CaO. Calcium oxide. Lithium and nitrogen is going to be Li3N. Lithium nitride. Aluminum and oxygen is Al2O3. Aluminum oxide. Or if you are European, aluminium. 109. Element X reacts with element Y to give a product containing X3 plus and Y2 minus. Is element X likely to be a metal or a nonmetal? It is going to be a metal, okay, because metals form positive ions. Y is going to be a nonmetal because it forms a negative ion. The formula of the product is going to be X2Y3. You just bring the charges down. What groups in the periodic table are X and Y likely to be in? X3 plus, it's either going to be here in the first column of the transition metals, or it's going to be here in the boron group in the P block. And Y2 minus is going to be in the oxygen group. Finally, 118, one more page. Iron is commonly found as iron, iron 2 plus, and iron 3 plus. Write the configurations for each. Iron is argon, 4s2, 3d6. Iron 2 plus is argon. Again, you can't see what I'm writing. Okay, I gotta get... Boop. Is argon, 3d6. And iron 3 plus is argon, 3d5. What are the N and L quantum numbers of the electron removed going from 2 plus to 3 plus? N equals 3, L equals 2. The third ionization energy of iron is positive 2,952 kilojoules per mole. What is the longest wavelength of light that could ionize Fe2 plus to Fe3 plus? Okay, so how much energy is needed to remove that electron? Okay, so 2,952 kilojoules per mole. All right, so E equals h nu, or hc over lambda. And then because it's kilojoules per mole, we have to throw Avogadro's number in there. So we have the energy, we have H, we have C, we have Avogadro's number. We're looking for the wavelength. So lambda is equal to HC in A over E. So the wavelength, we'll calculate it 6.626 times 10 to the negative 30. I'm blanking. Is it 1 or 4? I think it's 4. Joules seconds times 2.998 times 10 to the 8th meters per second times 6.022 times 10 to the 23rd per mole, all divided by 2,952. That's kilojoules per mole, so I'm just going to go ahead and turn it into joules by multiplying by 1,000 joules per mole. All right, so I'm going to go ahead and double check the signs, or the units per seconds cancels, joules cancels, moles cancels, and that's going to leave us with meters. Good. So I bring up my calculator. 6.626 times 2.998 times 6.022 divided by 2952000. All right. So negative 34, that's positive 26. No, negative 26, excuse me. Then we had 23, so that's going to be negative 3. So our answer is 4.052 times 10 to the negative 8th meters, or 40.52 nanometers. That's a very short wavelength. And that is going to be the longest wavelength. Any longer and the energy goes down. Okay. But I want to double check my math a little bit. I want to pop back. Okay, so we're on page 135, so I'll pop back to the appendix, double check my work there. Because obviously I am kind of fuzzy today. I don't want to leave you with wrong answers. 118, need to go another page. 118, what is 40.6. Okay, good, I got it. The electron, okay, so we go back to page 135. Okay, finally, last problem of the evening. The third ionization energy of ruthenium is less than the third ionization energy of iron. So ruthenium is directly below iron, so there is no mystery there. It is easier to remove an electron when you're removing it from a higher energy level. Higher energy level, the electron is just further away. Whether you're talking about the valence, the outermost valence electron, or the other electrons, regardless, the electrons are just further away, so they're going to be easier to remove. Okay? Just really straightforward, really simple. All right, that's it for Chapter 3. I will do Chapters 4 and 5 on the morrow. I've already done the lab for this week, so I guess Sunday is when I'll start doing Chapter 6. Okay, I will see you around. Have a pleasant weekend. Good luck on the test.